Today's iteration of the data-driven science and engineering seminar series. Today we have the pleasure of hearing from Professor Boris Kramer in the Department of Mechanical and Aerospace Engineering at UC San Diego. Professor Kramer's work spans a wide variety of fields, but focuses especially on model reduction for surrogate modeling, system identification, control, and certainty quantification. And today we'll be hearing about data-driven reduced order models and applications to control the soft swimming profile.
Okay, thank you so much. I see some activity on the chat, so if one of you guys, you're on it, okay, so if there's any questions or people can't hear me, please let me know. Thank you so much for the invitation. It's my second time at UW. It's been fantastic already. I'm trying to talk today a little bit about some work we have done in reduced order modeling, but also targeted going towards the direction of digital twins. And I was hoping that this would be of interest to this audience. It has a little bit of a mechanical flavor. So if some of you are more on the engineering side, there's some experimental stuff, and some are more on the modeling side or learning side, there should also be something. Yeah, so let's go with this one. Collaborators, just want to acknowledge my former postdoc, Harsh. He has been instrumental in the modeling side of this whole thing. Iman is Mike Tolley is a professor in robotics in our department. He runs like a soft robotics lab, and Iman is the grad student who has done most of the work here on the implementation side. And I also want to acknowledge the funding. Have a couple of videos here. At the risk of maybe some of you having seen this, I think Steve may have seen this, right? People have seen this video before? Many times? Okay, everyone's nodding, cool. Kevin, have you seen this video? You have not seen it. Okay, so you're going to be the guinea pig today. So what's happening? Did you pay attention? There's a fish swimming, and it kind of swims upstream. And, if you have seen it, it's very boring. But if you haven't seen it, the crux of this whole thing is that the fish is actually dead. They put a dead fish in a channel and let it swim upstream by doing all of this morphological bending and basically zero energy control to go up. And so the idea, this is what really motivated people like Mike Tolley to start looking at anguilliform swimming, eel-like swimming. And so what they have done, this is an older iteration of a fish that they're building, the Serpent Mini V0 or V1 at the lab. So what you see in this fish, it has actuation. I'll go more into detail. We have actuation in these chambers. We have rigid couples in the middle, and we have several sensing things. So we have a built fish. What I really want to do here, go from a built fish to a model to a controller. So the outline of the talk is as follows. We're bio-inspired. We have seen these eel can swim up. They're very efficient. We want to do for naval applications, to be able to swim for a very long time with a very minimal amount of energy. Mike has designed this soft robot to do some of these things. That's where we started. Then we said, well, wait a minute, let's take this model and try to do some modeling of it. So let's go from here to a mesh, from a mesh to constitutive laws, and from constitutive laws to finite dimensional model. Unfortunately, controlling the nonlinear thing in very high dimension is not possible. So building surrogate models, I'm telling you about this, comparing a few things, and then we plug this all into a control design, tuning of a model predictive controller, and then we kind of run it back. Okay. So that's the outline of the talk. For better or worse, we stuck with somewhat classical techniques, linear inference techniques of these three kinds. So I'm going to show you some comparisons, and we look at the end a variety of different tests that we made for that. That's the outline of the talk. Okay, safe autonomous vehicles. Like I said, Navy is very interested. Other people are interested in this. Challenging is you have infinite. It's pretty nice for a computational person because, robotics used to be a very low-dimensional field in a sense. You had very few degrees of freedom. Now you have continuum robots, right? Infinitely many degrees of freedom. They're hard to control in real time. They're also fundamentally under-actuated. I mean, we only have 6 actuators on this whole thing. Actuator design in the robotics community is a big deal. We're using basically fluid elastomer actuators that kind of have an external pump. You can see some of these strings here, and they kind of pump fluid either on one chamber and suck it out of the other, so they have a plus-minus antagonistic relationship. You can also do Hazel actuators, which are contracting muscles. They're a little bit more tricky to deal with, but that's also common. We just stick with one type of actuator. That's the one we've implemented. And then other things we have to deal with is, of course, like in order to get this little twitch motion, you need many of them, but we can't have infinitely many of them. So then we kind of build chambers of, certain size. So here we only have 3. Of course, you'd like to have 100 of those, but then you need 200 controls, right? So anyways, this is kind of what we have here. They built the silicon molds, modeled it, have the geometry in CAD, and then have a FEA model. Nicely, there's a software called SOFA, which is really a cool modeling software in C++ for soft robotic modeling. It's just a little complicated to set up, but it does the job of what we need to here. This is our fish, just for orientation, coordinate system. We have 20 points on the center line. We either mark them on the experiment, so we have cameras and we can track where the points are, or of course we read them out from our mesh. These are our chambers. So we have 40 outputs and we have inputs, technically 6, but really we always choose this to be minus that. So it boils down to 3. Okay, so 3 input signals I'm going to have to design. So now we said, okay, what are we going to do? We can't work with the finite element model. It's nonlinear, it's high dimensional. Let's do something. So in the first part, I want to just walk you through a little bit of like reduced order modeling, some methods that we had already developed at the time, and then we're kind of ready to use on this problem. So I just want to step 5, 6 slides through this method and then kind of show you how we used it. So here's a Lagrangian model reduction in one slide. If you have Lagrangian mechanics, it basically boils down to like you have a Lagrangian function going from this tangent space to the reals. So it's a scalar function. And you can write down the forced Euler-Lagrange equations as follows, where basically the Lagrangian defines this equation, and you can allow for external forcing if you want to. And of course, we have external forcing here. This is not simple in colloquial simple, but simple in the terminology of geometric mechanics. So if you have simple mechanical systems, in this configuration manifold, you can actually split these, and the kinetic energy depends on x dot, the potential depends on x. And if you make a lot of simplifications, you can even write them as quadratics. And then you have this constraint that you have positive definiteness of the M matrix. Okay. Forcing here, we model forces to be linear as well, linear actuation of our chambers and dissipation as well. And then you end up in this framework with a simple model that you have seen in engineering mechanics undergraduate curriculum for a while. Nevertheless, so if you start here, you can write the system down. You don't know anything about, let's say, M, D, K, or B. If you start from here and you actually interpret them as energies, then you start noticing that M, for example, has a symmetry and that K has to have a symmetry. You wouldn't know that if you just look at this equation. Okay? So now this is the full order model. This is how you get to your full order model simulation or your full order model. What has been done? So intrusively, and in the model reduction world, there's 2 things. If you have this code available and you can go in and implement projections, then we call this intrusive model reduction. Lal and Marston have worked on this in 2004, kind of outlined some steps to do. And then Kevin has worked on this 10 years ago in a previous research life on the intrusive side, also for structural problems. They're all intrusive. There's other structure preserving works. I stopped at 2020 here, but there's much more coming now. You can do structure preserving Lagrangian neural networks and other things. Of course, you need to do some sort of dimensional reduction because many of these things at the time were not having had a very low dimensional input layer. Then on the non-intrusive modeling side, you can do all these things. You can do DMDC, you can do eigensystem realization. We'll do that later because it's very, very popular in engineering. Operator inference, lift and learn, other things. They all don't have Lagrangian structures. I could go on for like 5 hours now talking about how many modeling methods you could use. And then Peter Bennett's group has also worked on some second order systems, like without quite a mechanical structure here as well. Kevin.
But not like generally nonlinear potentials that are not just quadratic for the operator inference side of things.
I'll show you those. We have. Thank you for the segue. Anyways, in 3 slides, I'll have it. Yeah, this. I kind of asked Kevin to come today and ask some questions. To like the ones that I would like. Exactly. Thank you. Okay, so what we do in this business is pretty simple. We stack snapshots. All of you have done this. You collect simulation data, X, Y, U. So you need to know what inputs have driven your simulation. You measure outputs and states. We do linear reduction here. So we use an SVD, old classic. We get reduced states, and once you have reduced states, either you have reduced derivatives or you just process them very high. So we're assuming no noise here. You can of course do like total variation differentiation or other things, but we just use like very high order finite differencing to get derivatives. But there's a way to get derivatives, let's say that. Things look very easy here, but I just want to motivate them. So now we say, hey, at the reduced setting, we're going to have a Lagrangian system. Very simple. Even the M matrix now becomes the identity. The forcing is all linear. All that stuff's very, very general. We just enforce that, and by enforcing this, we automatically impose symmetry conditions. And so now I hypothesize that this is my model. What does this boil down to? The learning case, this is a really interesting case. You have second order dynamics. You have X double dot. What you don't know is your basically your D and your K matrix as well as your B matrix. What you do know, however, that these D and K matrices have some symmetries and they're positive definite. And B is something that just tells you where your inputs are actuating the system. Okay. Okay. So I'll relax a lot of these assumptions in a bit where we learn general M and we learn nonlinear things. But right now, let's just say we're doing linear things. You can solve this with semi-definite programming, and then you back out your output matrix just like you would do in any other method too. Okay. And we have done this in other soft robot applications. One of them I'll show you today. And so now, Kevin, this comes to your questions. What do you do if things are nonlinear? Of course, now you can start using nonlinear parameterization. So either you can learn very specific forms, or you just parameterize the nonlinearity a certain way with a network. So we've also looked into this. The issue here in the previous formulation is this is a really nice formulation if you don't let the mass matrix to also be a variable here. If it is, then you get the trivial solution to be the solution. So that's not good for optimization. So we first optimize over this. And then the second step, we correct the mass matrix through a network. So basically now you would say I have a general nonlinear Lagrangian systems with nonlinear potentials. And you have them here. And these are parameterized now by MLPs basically, and polynomially augmented because we suspect that low order polynomials will continue to show up in these, which they do. So in the first step, we do a two-step approach. In the first step, we just learn the linear dynamics. That's the prior for learning the nonlinear corrections to that in the second step. Okay, and all in a Lagrangian setting, making sure that always the energies are ensured to be positive, and that we have symmetry. We basically get this M matrix by taking the Hessian of the potential that we learned. And that way you know that you have that, okay? All right, so that was just a Lagrangian method, very, very simple. We actually kept everything linear here. I mean, I showed you this, we have done this nonlinearly on structural mechanics, on beams and vibrating structures, but even if I had a nonlinear model, I would have to control it some way online in a processor, and we kind of like to have linear models there hooked up with controllers, okay? So this is an extension not used on the soft robot here at the moment. Okay. So now Daniela Roos is very famous in soft robotics and robotics in general. They looked into this up at MIT in like 2012, 14-ish. They started developing these small little fish. You see this one only had basically one actuation mode here. And this was their rigid couples and then the head that basically couldn't move. And they actuated, and also this was kind of the starting point where many of these designs came from. And the one I've shown you had multiple segments now, right? But you could get really nice bending moments here. Okay, so this was the first model. Then Thomas Meurer in Germany, in Kiel, kind of took this model, discretized it. You can download this if you want to at MoreWiki, the website. So this is a linear model. That their CAD model has about 800,000 degrees of freedom. Implements basically linear constitutive relationships here. And it's the same thing here. It's these tubes here. The tubes come in that bring the fluid into these chambers. Everything has a hull around it. And then you can basically create these bending moments, right? And at the center beam, you're measuring here the deflection. This is really the deflection that requires you to that gives you thrust, right? That's the main movement you see in these fish. Most of these fish actually move with having a fairly steady head, but then a lot of actuation coming more on the tail side. Okay. Equations of motion, pretty simple here. At least we don't do any fluid structure coupling. So right now, this is just the structural dynamics of it. You have a governing PD, you discretize it. And now we run some experiments. So we did this Lagrangian operator inference. We generated data of this simulation. This is a linear simulation, so it doesn't take too much time to run it. Now we do sinusoidal input. The black line here is indicating the end of our training. So we train for about 0.4 seconds, and then the rest of it is testing. That's the only data we've seen. You actuate the system. We created a. We only needed 2 modes to do this. This was a fairly simple system, okay? And then we start actuating the system from 0. We start driving it with sinusoidal input, and we kind of match this pretty well. Okay, so this is the first one. This was sinusoidal. Then we did sigmoid input, also tracked reasonably well. You see the displacement here is not bad. It starts decaying because it starts dying out. Here we had to train for about a second, so we could predict about 100% out. And then lastly, I did a step input, which was an input that was not seen in testing. It was in training. It was trained on sinusoids, and then we used a step. You see, if you drive the step input, your energy originally, when you insert this energy, it kind of spikes up, but the model eventually recovers, and then it recovers nicely and just remains stable. One of the great things about enforcing structure is that you have stable simulations, and you retain some of the physical properties that you have, interpretability, for example. Okay, so this was all the linear model. This was just kind of a precursor before we started working with the robotics people. Now, this is the first model that I will use later on this actual fish. A second model that the grad student came to me and said, well, one of the things people use is ERA. I said, okay, use it. Eigensystem realization, very, very well used in the community, over 40, 50 years of research. It requires technically you to do what's called an impulse response measurement in discrete time. So you kind of have to excite every channel and then see how the rest goes. If you don't do that, so if you have a more broadband, if you have a signal that has, not just impulsive, but a more general signal, then you have to do something else, this observer-Kalman identification step. But you can combine both of them, and when you do both of them, then you get your basically linear model out. This is very classical stuff, don't want to talk too much, but you have a matrix of Markov parameters, you shift the matrix of Markov parameters, you compute an SVD of that, and then you can back out the B and the C matrix by reading things out, and the A matrix by doing a little bit inversion of the leading Hankel singular values, okay? So there's inversion, and you have to choose a reduced model dimension, but fairly standard to use this. The one thing to keep in mind here, it works for like a single trajectory. So here you're collecting data of one trajectory. So you have multiple data sets. You have to think about what you do. You can't just add Markov parameters or do something like this. So you can fit multiple models, for example. Whereas in like SVD-based approaches, you can just stack all bunch of data into a big data matrix and take an SVD. Here you can't do that, right? So when we compare with this method later, we'll just compare this to one trained data set versus in SVD-based methods like in DMD or in operator inference, I can train on 2 or 3 data sets. Okay? And then lastly, DMDC, don't have to preach that here. You know how this works. We just fit a model to the data that we already have. ABC. Mind you, DMD's ERA is the only model that spits us out potentially a D matrix, which is the Markov parameter here. All other models don't have a feed-through matrix. Okay, okay, so nothing new here. Now, the more interesting thing now comes when we think about control synthesis. So how do we do our policy? I want to spend a little bit of time here. We start with the plant is our simulated robot, right? It's the finite element model. This is not really control affine, but we have a linear output. And then it produces an output, Y. We will do reference tracking. So there's a reference given to us, a reference which is a biological, like a bio-inspired trajectory that a fish could swim. And I'm trying to track that. So I'm trying to figure out if I can get my fish to do the same thing, right? So then based on that, I do a couple of things. First, I need to create a state estimator or an observer. We do Lüneburger observer here because it's the simplest thing to do. So that gets you an estimate of the state of the reduced model state. That's where already the reduced model will be used. So the reduced models, whether that's DMDC, Lagrangian operator inference, or eigensystem realization, will be used here, either with or without a D matrix to do the estimation. And then the state estimate goes into the control as the initial condition into your control policy, and then you do rollouts with MPC, and you're trying to figure out what's your best kind of short control that you need for the next several time steps, and then you kind of keep repeating that. I'll have more details. But that's the idea. You go from here to there. The one place where the physical experiment comes in is like the trajectories that we have here. Right now, we're still having the closed loop running on the high dimensional simulation. We don't have it on the microcontroller yet, so we don't have it on the fish yet. That's the next step. But basically, these trajectories are coming from the experiments that we have done. Okay. Good. So a little bit about the observer. This is probably the first thing you would do if you build a state estimator. You have your previous output, and you're looking at the reference state that's given to you. Like I said, D, there's no D here. That's the one that's the one that allows you to actually calibrate your reduced state. And then you do this. One of the things you have to do is you have to tune this L matrix a little bit. So you can tune the heck out of this if you want to, but what we just did is that we just wanted things to be, this spectrum of A minus LC to be in this range, and that kind of did the job for discrete time system. But you can play around with this. This is just gain tuning, and of course you can use a Kalman filter and other things. But Lüneburger kind of did the job here, and then we have the estimated errors. Okay, these become the initial conditions for the model predictive controller. So now what does the model predictive controller do? It tries to find a control sequence. So you're kind of at time step K now. You know what your control was from the previous time step. You have your best estimate of the state. This basically says initialize whatever the Lüneburger kind of gave me. So this is from the observer. You kind of know what your previous control sequence gave you, and you're trying to figure out a control from 1 to a certain horizon. So maybe 5, 10 time steps. And you do this by minimizing a cost function, right? So the cost function is now also rolling out from 1 to t further into the future. Your target is whatever you're trying to hit. This is your target trajectory that I would like to get, which is the bio-inspired trajectories we have. And then you're penalizing, of course, from that, but you're also penalizing how much control input you need to do this. And you're kind of penalizing a little bit of this difference. So you don't want your controls to jump too much between time steps, right? So there's typically a little bit of a rate limit that controllers have and actuators have, and you need to implement that. And then inside, the reason this MPC works so fast is because you have a linear model. If nonlinear MPC is a whole different story. We upper bound the controls by a U max, which is the max pressure that the pump can actually have. And we have antagonistic constraints. We technically have 6 controls, but really we're just learning 3. The other ones are just a negative. Okay. So that's the online MPC that we're solving with the reduced models. So now we're solving them with like 3 different reduced models. Okay. Okay. Trajectory. So what would we like to track? That's the first question. So we generated, we have 3 different tests, and they get increasingly complex. First, we generated 40 data sets of about 10 seconds of this fish swimming. I'll have a slide on this next. They're available online if you want to download them. Again, there's finite element simulations about 250,000 degrees of freedom, nonlinear. And yeah, they were ran with the SOFA toolbox. And now we do training. We have 40 data sets. We either train with 1. So this is my little table for training. And it really tells me I have 3 segments, the anterior, the middle, and the posterior segment. Do I excite them with low amplitude with a higher amplitude, and at what frequency? So if I'm over here at data set number 40, I excite all three chambers with the highest amplitudes that I have, which means I give them the most bending, and I excite them at the highest frequency. So in a sense, you would expect that data set to have the most dynamics in it, and you would expect data set 1 to be a little bit boring because you're not doing anything to the back, you're just exciting the front part, the anterior part of the robot at a very low frequency, so maybe a slower, right? So then we said, okay, let's take a mixture of this. We take when we train on one model, we always use this. When we train on 2 models, we use this and that. And if we train on 3 models, we're going to use this, this, and that. Okay. And then we do testing, and testing we do on 8 different ones of those, like on 39, 33, wherever you see the stars. These are my testing conditions. Okay. So testing means these simulations produce centerline trajectories, and those are the ones we're trying to track. Okay. A big issue in soft robotics is how do you know if a trajectory is feasible, right? So this is feasible for our simulation because we've already simulated it. The question is it feasible for the fish to swim like that? That's a whole nother question. We'll get into this in the next test. Okay, so we have 11 feasible simulations to test. Another thing you have to do once you do MPC, I didn't talk about this much, but here I had weighted norms. So you can kind of weigh how much you want to penalize certain control inputs, right? For us, since all of the pump was, I had 3 similar pumps, and they were doing the same thing. There was really no difference of penalizing one control different than the other one. So what we really went with is like that these control weights are the same for all controls. And we did some tuning, and after tuning, this is very standard practice in controls. You tune the cost function to get the performance. We got these following parameters for the penalty of the control, the penalty of the rate, and then there was a penalty on like the third direction of the state. Okay, so we did a tuning, and this is a point I'd be happy to discuss. So we kind of like tuned this on all 3 different reduced models, and we kind of see which policy or which of these weights work the best for all 3. So we could better compare. So we would basically have, now I can compare the same cost function for all 3 models. If you really want to get the ultimate best controller, you should tweak this to your, once you have a reduced model, you can go ahead and like tweak it again and create the best cost function for that, right? So it's a little bit of a question of what do you want to compare with? And this could be one thing that we may or may not change later, but right now we use the same weights for every reduced model and every controller and every reduced dimension, okay? Okay, so if you want to download it, IEEE has a nice data port feature where you can get like a little DOI. So if you want to download any of these data sets, they're right here. Just did that this week. Okay, this is yes? Yeah.
There's also a thing, right? Where you had, I mean, this robot said it was up at Daniela's lab.
Yeah, I mean, this was.
Video access to.
Yeah, we have uploaded videos here. So we have uploaded videos here. I showed a little video at the very beginning. So this is Daniela's robot that it really inspired the soft robotics community.
Yeah,
We have, yeah, no. We have built our own one more or less, which is this one. So this is at UCSD. Oh, you want a video-based learning?
I mean, take this.
Without this simulation model? Yeah, you can do that. Use some RL. We have videos of this. I have to check with Iman, but this is an older version of the robot. They currently have a newer one that actually has better kinematics, to be honest with you. And I don't know how many points they have on it. On this one, we had 20 points, and we have video data. I have to check with him. We're only using it as reference trajectories, not to learn the model. But let's talk, yeah. And I don't know if Daniela ever had videos of her robot up. I know there's snapshots, but I don't know how publicly available that data is. This is Daniela's one from like 10, 12 years ago. Okay. Okay, so we're hanging out somewhere here in the control sense of this. Tuning, talked about how we generalize. Data set available, so videos are on there. I just have to make sure that the markers would be there. So I'll check with a grad student, with Iman. So this is what Iman calls open loop outputs, which is open loop outputs are literally just give me a control sequence, give me a forcing and run the model and see how good the ROM tracks the FOM. Closed loop is how good does the observer estimate the state. So there's no control here yet. It sounds open and closed loop, but there's no control here yet. It's just closed loop observer in a sense, like observer run and open loop. And a lot of data, I don't want to point you to all, really what matters later is once we hook them up. But what you see, we have these three methods. You can either train them. So here's model dimension. So we had three model dimensions, 2, 10, and 18. 2, 10, and 18. These are using one training trial, 2 and 3. And then you started seeing either running in open loops, so pure prediction, or in an observer setting. And the main thing I want you to take away here is that these models, and you see this for what reason, oftentimes we're off by a little bit in the phase, and all of a sudden these time domain things just don't notice that, and they look like they're horrible, but they're just off a little bit in the phase. So don't make that get you too nervous. What we do see that in closed loop operation, all these models are doing much better than they do in open loop. The other thing is like training on multiple trials. For some reason, I couldn't get DMDC to get better when it had a third trial. But in OpInf, we did a little bit better. But I think you would just not do that and just pick that model, to be honest. Okay, so increasing data kind of helped for these two methods. ERA, I mentioned, can only be trained on one trajectory unless you want to do operator interpolation afterwards. Okay, so now we look at this thing again. So these are, again, simulated trajectories. So we have this point here, and we're starting to look like at these point-wise estimates now. So how far are we off of this point from the reduced model in the actual simulated trajectory? And what we start seeing, this is pretty close to the head. This is a center line, and this is at the back. These are the trajectories that we start seeing. This is typical fish swimming motion, right? So you start at 0, straight out, and the fish starts exciting, and you see a lot of movement at the tail, right? So the tail, we have the highest amplitudes here, 50. You see here we have smaller amplitudes. There is wiggling in the head, so you get about 25, but in the middle segment, you're pretty steady. The largest amplitudes happen back there. That's also where, it's most important to generate the thrust, okay? And so you see, like I said, the errors are somewhat misleading because really the metric we should be measuring is produced thrust. That's what matters at the fish at the end. You don't have to exactly mimic the shape, but this is what we have right now. Okay. Most important things is that, we trained on 1, 2, 3 data sets and we tested on 8. So these errors are all averaged over 8 data sets. There may have been one where it's perfect, but there may have been one that was pretty bad. Okay, other things that we have here. Good. So now we move into the space of like, this is something that someone, there's a really nice paper by Teitel and Lauder in 2004. I have the link on there. I'm not going to click on it now, but it's just a 5-second video. So they actually did PIV measurements of, they had, a little water experiment. They had this fish in there, did PIV measurements to actually resolve the flow field around the fish. Because really that's what you need for the fluid structure interaction, right? You're trying to see how the vortices created by the fish create thrust. And so they did this stuff and they parametrized the motion of this anguilliform swimmers basically with this function. So that gives you a very simple function to just plug parameters in. You look at the tail beat amplitudes, growth rate of the amplitudes, frequencies, and weight and body wave number, and it gives you, I think, about 12 data sets. So now this is something that, like I said, empirically has been observed in experiments in the wind tunnel to be a shape that's reasonably well parametrized of that. So now we want to see, can we track that one with our robot? Actually, not with a robot, to be honest. Can we track it with the simulation we have? Okay, so here you see the swimming motions. These are swimming motions over 10 seconds. So it starts out straight and then it starts bending and then it keeps bending. So these are all the possible swimming motions at this parameter value of alpha being 1.0. And if alpha is 3.5, you get more of the tail beat amplitude is larger and the fish swims more like that, right? It doesn't use the whole body torsion. It just uses the back of the tail more. So now if we zoom in here, if we look at, also as a function of these wave numbers and whatnot, you still continue to see You continue to see high errors, but like I said, I believe this is all due to the phase switches. But what I want you to look at is like, what kind of trajectories are you starting to see? You see that these reduced models, ERA is kind of doing the worst job in getting some of the dynamics in the tail end. DMDC does certainly better. And in Lagrangian operator inference, we're also doing pretty good to get all of these movement. Okay, this is dynamically somewhat feasible. Like I said, one of the issues we continue to have that is if you really want to track all of these, your controls are actually starting to hit saturation limits. So that's an issue you have when you hit saturation. When you go over them, you have issues with numerical stability of the solver. So if you get very strong controls, so there's some things in the implementation that maybe would be smoothed out if you just work with a pump that has delays and inertia, right? Okay, so now we're going to the third one. So these are, Nathan, these are videos that are literally just reading out these sentences. So this, I should actually show the whole fish, but this is literally the whole fish in the tank, but reading out now with post-processing just the markers that we have along them. So I'd have to check if you want the whole fish, if you want to learn something 3D, then we would get this. Otherwise, these videos we have of the center marks, right? In soft robot modeling, there's a lot of different theories. I mean, we're doing like 3D finite elements here. A lot of people use like 1D Kosarat theory, and then you could kind of like start with that, okay? Okay, so here's the eel. This is what they observed now. So in their videos, so they just overlaid videos and kind of showed that for these, I don't know why this did not compile right. For these different lambda values, they get, different motions. And here they were trying to focus a little bit more on like a tuna style swimming. I'm not that much of an expert in fish, but apparently they have different ways of either using more head center and tail excitations. Okay, so these are all of these, and now we have them. There's different wave numbers that they can be characterized in. And depending on how you choose those, you have either more of an anterior focused or posterior focused or entire focused bending moment. Okay, so these are now, so now is another thing. These are coming from my robot. My robot and my simulation are not the same thing, right? There's a lot of assumptions we made to get to the simulation models. So we don't fully know if they're feasible to be reproduced in simulation. And what we see here is that, here, for example, would be some of these. You see extreme bending at the back here. Now we actually only compare best case controllers. And it was interesting that, for example, DMDC selected the R equals 2 model as its best model to perform in ROM. And in Lagrangian operator inference, we used like an R equals 18 model. So very different in how they compared. And I haven't studied that further. But we're basically looking at like the orders that we get here for different, different motions of the fish. And we're starting to see, of course, that the tail, as you see, moves the most. So we have the most amplitude here. And you're starting to see that we're getting part of that, but really this is what the simulations are giving us, right? The simulations closing the loop with the simulated controllers. But you see they just never hit the amplitude quite right. And this is because we started hitting like limits with our integrators. So this is certainly something we have to get better at to get more amplitude in the models. And this applies to all of the models we have. But overall, it's quite encouraging that most of the ROMs are doing pretty well, with one doing a little bit better towards the tail, but most of the errors are happening at the tail. Okay. All right. And then you start seeing, so now I said, well, can we just look at the control signals? Like, what did we actually compute? And so, mind you, we have 3 chambers or 6 chambers and 3 controls. When we generated the videos in the water tank, these are the nominal control signals that were fed to the pumps. First pump and then most excitation in the rear end, in the posterior of the fish. And so these are, you can read out the phases and the magnitudes of those. That's a nominal. This is actually not, we don't have in this version of the fish, we don't have a pressure gauge. So this is not in terms of pressure. This is the electrical signal being sent to the pump. So I don't really know what the pressure is of this. That's the next thing. In the next version, we already have a pressure pump, but I don't have the data yet, pressure gauge. So this is kind of a proxy. Here we're actually in our code, these correspond to pressures in these chambers. But the main thing I want to show you is basically that step function-like behavior that we have, the amplitudes, the phases. And now these are the control signals that the ERA-based MPC produce. These are the ones that the DMDC MPC produced. And these are the ones that LOPINF produced. You see all of them hit saturation. So we're hitting these bounds. We calibrated at a certain point. Some of them saturate more than others do. We see that both of these are doing the best in matching the phase, at least part of the phase. So if you compute a spectrum of those, you're pretty close to that. Amplitudes we're not getting perfectly correct because we can't match the nominal with what we have here at the moment. And ERA just doesn't produce anything it just switches too often and is a little bit too erratic. Pressure constraints are most likely the issue that we have right now in creating dynamically feasible trajectory, or to be able to track this, because once the constraint goes on, I just can't get the next bend, right? Yeah, so frequency, we kind of get this right. And then phase shift. Okay, so I really wanted to show you today, like somewhat, we have done something, but it's clear that there's a lot of ways to do things better. This is not the project where I'm like, I have done it, I'll walk away, I'll work on something else. This is something we want to work on the next 3 to 4 or 5 years, and happy for any type of input. Probably all of you at this point have had thoughts of like, oh, couldn't you do this? Or couldn't you do this? Or there's some place to improve. And we're thinking about some of these things too. So I've showed you that we're trying to move towards a digital twin. We have this platform, we have sensors on it. We're trying to get more data from the sensor. And ultimately, use that data to also update our simulation model. So there needs to be some sort of a bidirectional data stream. We got an MPC policy. We did kind of like this Lagrangian theme of like getting a reduced model that guarantees the structural dynamics properties in second order form. And it kind of seemed to work the best. Future work is manifold. There's many, many directions. Each of them could take up a paper or two or a PhD thesis, to be honest, if you really implement it. We do want to think about nonlinearity, because one of the things that kind of seems to not get us dynamically feasible is that we don't fully match the nonlinearity in the system. Of course, also the estimation can be improved. We use Lüneburger, we tune it a little bit. We can use extended Kalman filtering if we do this. A lot of the work that Mike's doing is improving the actual physical twin to get better actuators in it, and to just create a fish that can more fluidly move, that doesn't have as many rigid couples. We need to implement the control. There is a control module implemented. I just need to get it into closed loop. And then the Serpent 2, they just told me this week that we have a nice oceanographic testing facilities with a lot of options to test basically water conditions, rough sea conditions at the Scripps Institution of Oceanography. So they want to put this fish actually not just in their little lab tank in mechanical engineering, but go over to Scripps and test it over there. And then we can get a little bit more interesting data of that response. The biggest problem if we want to stick with simulational stuff is that actually right now we don't have any forces coming back from the fluid. Our fish in the experiment swims in fluid. So it means that, of course, by displacing fluid, you generate thrust. Our simulation swims in a vacuum, right? So you're not getting that part of thing. And frankly, that's another thing. You might create a lot of interesting dynamics in the simulation that you wouldn't see if you were in water, right? That kind of pushes back against you and doesn't allow you to do these things. So that's another area that we're thinking about. But FSI for 3D finite element fish has not really been done. So this would be another area to look into. If you're interested, Iman just managed to put this up 2 days ago. You can read in this. There's also the data set and a couple of more methods papers along the way. And I think that would probably be it. I'll just leave it here with 2 more of these videos. Like I said, what we have, the dead trout swimming upstream. And in case there are any undergrads advertising that we're always looking for students to kind of continue this work, okay? And we are pretty close to an oceanographic testing facility. Worst case, we just throw it in there. Okay, thank you. Questions?
I have a question about the flow they're tested in because
Say it again at about
the,
what?
the flow,
Uh-huh.
is it like, are they, all the tests done in like still fluid or do you feel? Okay.
Yeah, they don't have a way to generate waves right now in the mechanical lab. That's why we need to go over there to actually create a stream.
Yeah, that's what fish do, right? They like optimize their technical base. So,
Exactly what this guy did, right? Yeah, yeah.
so that's like next step.
Yeah, 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 100%. I mean, right now they're happy that that thing swims. And and we I don't appreciate all. I mean, I sometimes don't have the full understanding of all the things that this happens, but it's quite an endeavor. Yeah, even fabrication, like what material use, how did you do the cast, how you do the molding, how do you put them all together, how do you couple it, how do you make sure it doesn't leak? So there's a lot of things you kind of have to do. But yeah, so many more avenues. Mike has a Muri on this, or I mean, he's part of a Muri on this. So they're continuing to work on like having new iterations of the fish. But yeah, I fully agree with you. I've sent him my wish list. Yes, you have a question?
Filled out that one. Speculative. So like just inspired off of this. So we know that, fish have a controlled actuation of their muscles, but they also have environmental forcing, which is that like vortex shedding if they're going up a stream. So something that I found very difficult in doing the data-driven models, even for linear models, is taking into account environmental forcing if you can't directly observe it. So just totally speculatively, like what are your thoughts on that? Because I understand that's not what you're doing yet here.
Right.
Yeah.
Yeah, that's a fantastic question. I think the place to go to is really this paper, this Titel paper like 20 years ago that really put this thing in a tunnel and did, just did PIV measurements to get the flow field idea, to get an idea of like what the flow field and what the forcing is. There's some other work. There's a person down in Florida that has a very high-speed camera to resolve flow physics in soft swimmers. And then mostly they kind of take that and then try to parametrize and come up with a simple parametrized boundary condition that you can then kind of impose on it. But it's very clear it's a super hard problem to impose the fluid on the realistically, right? Unless you want to just do the full coupled simulation, which we all know is pretty expensive. Yeah, so speculative, we're probably hoping to get some parametrized empirical models for that boundary condition. Because I don't think we have the fluid set up right now to get the full 2D flow field. Yeah, that's my feeling. But that's one of the big open issues in this underwater space for robots. Yeah. Nathan.
The development of like sort of, they put on cars aero rigs. Is there anything like that you could put on? Have they considered that? I don't know. You're in the space.
Tell me more about this. What is it? What is it?
Aero rig. Car,
Uh-huh.
plane.
Yep.
It's just basically like a rigid structure where you have a bunch of pressure caps all around to drive the car, so you get a sample of flow physics.
Ah, yeah.
outside. So it's try to make it very low aerodynamic impact, but then it allows you to sample the flow around the car. Imagine if you put this near the head, you could at least get a sampling of fluid coming towards it, some estimation of the flow physics that it's in.
Yeah, so this is a bit above my experience, but one of the things that they do in this Muri, I mean, one of the big things, I mean, they're roboticists, they build this stuff. Lagrangian operator inference is not part of their business, nor are they overly worried about this. What they're worried about is building a fish that works pretty well and does exactly what you said. So they're working on these in fish. I mean, fish have an interesting way of sensing. They do have like, there's these like micro hairs that you can use. And so what they're working right now is like putting these little hairs out, whiskers, so to speak, and you put them along here to get an idea of the flow fields. To make a sensor that's that small and measure something reliably is super hard. So one of the teams in the Muri is doing exactly that, with, of course, the ambitious goal to just peel a skin over this thing and get a full sensing field. So maybe I think they're in year 2 or so. So maybe by year 5, they'll be somewhere. But yeah, that's super exciting. I mean, just getting more information of that. I'll relay what you said about putting it to the head. Like, maybe that's something they haven't thought about, but they certainly are thinking about putting it on the skin. But reliability, of course, that sensor would then have to last like quite a long time. Yeah.
We have a question from the chat.
Yep.
How would you add nonlinearity to the system, adding external forcing? And would the methods here be still applied for a nonlinear model?
Yeah, sure. I mean, we can add a lot of nonlinearity. I was talking about this a little bit at the very beginning. So we do have a method ready to go, frankly. This is a nonlinear Lagrangian reduced order model that's parametrized that starts from the linear Lagrangian model and augments it by polynomials of cubic and quartic order and everything above MLPs. So we have a Lagrangian framework for this. But even if you have a nonlinear model, you got to think about it. How are you going to design a controller? And it has to be real time. It has to run on the microprocessor. And so are we just going to linearize this thing again and do MPC? So I think it's a question that we started from the back end and said, like, how do I want to have my controller? Where do I start from a controller? What kind of model would be reasonable? There are also energy shaping controllers. So you can actually design a controller based on a second order structure directly. We've also started looking into those, but then the implementation of that is another issue. So many interesting questions around this space. For the person that asked this question, we can do it on the modeling side, but we don't quite know how to do it on the control side. Yes. Yes. Uh-huh. Yeah, there was one of those. Yeah. I had one. This one? Yeah. Test. The green one is the training. Yeah, oftentimes I just train on one and then I test on whatever I want. Yeah, I'm not in an 80-20 situation here. I'm like, I don't know, in a 5 to 95 situation. Yeah, we wanted to be a little bit, I mean, I didn't want to overtrain and just throw everything at the kitchen sink at it, but I certainly could train on more. What we have seen more here is actually that using much more data, because we had in the highest data set, you already have a lot of the dynamics that you're probably going to see down here as well. So we didn't quite get all the benefit. In Lagrangian operator inference, it kind of helped having 3 data sets to drive the errors down. You still have variance across these 11 tests, right? So this is showing you the variance in the tests. It's just showing you the mean error that we have. But in other methods, it really didn't help, like doing more trials. Yeah. So yeah, I don't know. I feel like we already have a pretty broadband excitation in what we have here to give me this is many cycles of the experiment, right? I mean, so we're going for about 10 yeah, we're going for about 10 seconds of data. Yeah.
This may be an ill-posed question, so bear with me.
Is that the one I gave you last? Is that question too? Ah, okay, yeah.
So the AI community, there's a lot of focus on like sticking with canonical modalities like video, audio, that you would typically imagine AGI systems being equipped with to do everything, right? To like infer the scene, understand like intuitive physics, be able to plan and control from that point. How far, in your opinion, I mean, obviously that's a huge leap forward from like having like these specific sensor measurements, but if one were to like try to tackle a problem like this using more like scale of commoditized sensing,
Yep.
how would you think through the roadmap to get there?
Good question. There's a person working on this stuff, Christine Ellen Blanchette. She's at Princeton. She has taken video data of like, the pendulum, inverted pendulum, and reads that data into Lagrangian neural networks, and then is able to make predictions, basically detect that this is a second order system, stability properties and so forth. I think they have not coupled it, they have not done this in high dimensions at all. So like they kind of come back out a 4-dimensional model. So I haven't seen how this would work in high dimensions yet from video. The other thing is that I think, yes, we can kind of the question is, do I really have video when this thing is swimming? Right? I can build in the digital twin world, you can say like, I'm building this fish, I'm testing it in my tank, taking all kinds of videos, I'm training my model. Later on, you would like to update that model with like other things. And so there, I think you're probably going to have more like traditional sensors when this thing is swimming, 500 meters underwater.
Like the star problem statement, like given an engineering system you build, I want to have cheap observations and maintain a continually updating model of that system that I can then deploy and do NPC with. Is that sort of like the
Exactly, yeah. Yeah, we would like to have this thing underwater for 5 days, 8 days, 10 days, maybe come up occasionally to refuel. There's also ways to use buoyancy and energy to like energy harvesting systems in the open ocean. But to go as long as possible, of course, in order to do that, you need to do it with minimal control. To do it with minimal control, you'd like to do it in an optimal fashion. To do it in an optimal fashion, you probably need a model and you need sensors and state reconstructions are the things that Nate talked about. But I think the gold star would be to have this deployed with an onboard controller that's fast, 2, 4, 6 states, and that this thing can run very long without coming up. Kind of the engineering goal. Yeah.
I think we have time for 1 or 2 more quick questions.
And I'm around all day until about 5, so if people want to drop in. Yes?
Be possible to extract a force field from these hair sensors by taking a video of the shape. So if you kind of move the torch, sort of moving.
I haven't thought about this. I guess you could. The idea is that when this thing swims, you just don't have a camera on it, right? So you would directly, I don't know how they back out or what they back out. I think if they just can, I don't think they can actually measure displacements of this. I think they can start measuring like the velocities of their hair at the moment. I don't know if you can back out the force field. I guess you could, but the idea is to do it without a video, I think. Yeah, so that you in real time have a good idea of what your boundary conditions are for the simulation.
I have a last question.
Yeah.
On slide 20, yeah, right here, 26.
Okay.
You mentioned that you tune the weights across all different models. Can you speak a little more to how sensitive each model was to the weights?
I can't speak directly to it because Iman tuned it. But yeah, I can't tell you if like each model was like getting 50% worse because you changed these weights. I don't know. I'll have to ask him and relay that. That's a good one. Yeah. Yeah. I'm not going to speculate.
All right, well then, let's thank our speaker one more time.